Hi. Before we study regression estimation, we'll review the basic concepts of the simple linear regression. If you are familiar with this linear regression, then you may skip this part of the video lecture. Suppose that we have n observations of x and y, and the model is a simple linear regression model, and beta 0, beta 1 unknown parameter, and EI is error terms and with mean 0 and variance sigma square. The error terms are independent. One classical way of estimating the parameter is the ordinary least square method, and it basically minimizes the square of the error terms. And then this is mathematically this is a nonlinear function of two unknown parameter beta and beta 1, right? So we can it's quadratic function, so we can easily minimize it. So how to do it? Where you can actually compute this, right? So these two equation is equivalent to, so this is equation. So the first part, okay, so the first part, so this is just two set two equations, right? So first equation is this one equal to 0, and the second equation is xi equal to 0. So this is just the one way of writing the two equations using a vector. This equation is called sometimes called the normal equation. And if you solve this equation, so this is a linear equation, right? A system of linear equation of beta 0 and beta 1. So you can easily solve this, and the solution is this one. Okay. So that is the solution to the normal equation. And now, let's take a look at this total sum of squares. So if you look at this, you can always write it uh, uh, write this way. And so then summation, you can expand the square terms, something like this. 2 times right? And so the summation of this guy is this guy. That is a total sum of square error, sum of square error term. And this guy is a sum of square regression due to regression. And the cross product term is the cross product. So the cross product term is 0. And why? Well, I'm gonna write it carefully. So why the total sum of square term is 0? Well, cross product. The cross product is 0. So you can see that that is the yi minus yi hat and yi hat minus y bar. Okay, and yi hat is beta 0. Oops. Beta 0 hat plus beta 1 hat xi, and that is y bar plus beta 1 hat xi minus x bar. So you can put it this way, then you have something like beta hat 1 xi minus x bar. Huh? So you can write it. Okay, so something like that. So this guy is 0 and this guy is 0 because of the normal equation. Each normal equation here, right, this component, by the normal equation, these two terms are 0, so the term, everything becomes 0. And now let's take a look at this ANOVA decomposition. So basically, this sum of square total is sum of square error plus sum of square regression, and the degree of freedom is 1, and so the terms, okay, so if you look at the SST, right, so this one, you may think that this is sum of the square of this. So we have n of them. So we have n terms, but these n terms actually has one restriction. The one restriction is this. So that is the. So that means these n terms turns out to be actually sum of the n minus 1 independent terms. So the degree of freedom is n minus 2. Same way, SSE is hat. So this guy is what? Beta 0 minus beta 1 xi. So this term, and that is actually the residual, right? So let the residual satisfies two constraints. One is the first constraint, the other one is the second constraint is the. So the total among n, we have two constraints, so that's why we have n minus 2 degree of freedom. So something like that. So that is the typical ANOVA decomposition, and then mean sum of square is basically sum of square over each term divided by its degree of freedom. Okay. Okay. So that gives the the ratio of these two is the f value, and turns out that this f statistic will be distributed with 1 and n minus 2 degree of freedom distribution under the null hypothesis of the beta 1 equal to 0. By the way, I will so there's actually another way of okay, let me write it this way. So if you how you actually do a test. So I just, this is one way, use f. The other one is t, right? So beta hat 1 minus beta hat 0. So that is 0. So 0. Variance of the that is the variance of the SXX MSE. So that is the t statistic. MSE is this guy. Okay. So SXX is xi minus x bar square. So if you square them. Okay. And by the way, okay, so square them, then that is x square divided by MSE divided by SXX, right? So by the way, if you compare this SSR, so what is SSR? Sum of square regression. So that is the yi hat minus y bar square, and then that is beta. So yi hat is beta 0 hat plus beta 1 hat xi. That is y bar plus beta 1 xi minus x bar, right? So you can y bar cancels out, so that basically you have something like xi minus x bar square times beta 1 hat square, beta 1 square. So that the numerator becomes SSR divided by MSE, right? So that's exactly the F, because we have 1. So that is F. So the the t-statistic squared term is exactly equal to F in this case. Now another, let's consider the sample regression coefficient. So that is the sample regression coefficient. Let's write it so that you can call this one as a SXY, SXY. This one is SXX. This one is SYY. Okay, so that you can write it this way, and then residual sum of square is so if you beta 0 hat minus plus beta 1 hat xi, right? So if you write it this way, then basically you have something like yi minus y bar plus minus beta 1 hat xi minus x bar squared. So that is, if you expand it, okay, maybe I will, okay, so what happened? Okay, so let's first prove this one. Okay, SSE is I equal to 1 to n yi minus yi hat square is yi minus y bar minus beta 1 hat xi minus x bar square, which is syy minus beta 1 is sxy minus xxx. So if you do some algebra, beta 1 hat sxy plus beta 1 hat sxx, right? So that after a square, so in the end you end up getting ssy minus beta 1 square. Okay, so in the end sy minus square sxx. So you can write it as syy times 1 minus sxy square divided by sxx syy, which is syy times 1 minus r square. So that proves this part. Okay. Now, the t-test statistic, this guy is, so let's write it, sorry, double So to show this, so the t is beta hat 1 MSE divided by SXX, right? So now the we can write it as a function of r. So you have this one. So that means r times square root of the SX SYY divided by SXX. Okay, and this guy is SE divided by n minus 2, right? So you have SSE divided by n minus 2 times SXX. So then, and then I'm gonna use this SYY 1 minus r square. So if you look at this carefully, you can see that now you have this guy and this guy cancels, and this guy cancels. So the finally you can obtain that n minus 2 r divided by 1 minus r square. So that's very interesting algebraic result. So basically we have three ways of testing the same hypothesis. One is F, right? Use this one. Second one is the original t-test of beta hat. Third one is another way of using sample correlation coefficient. Okay, so that is a very brief review of the linear regression.